Okay, so this is the actual number version of number 2. It was my hint to go ahead and try this with numbers first. Remember, the question was, what percent of the height of a conical cup is the depth of water when the cup is filled to half capacity? So my suggestion was to go ahead and try it out with some numbers first and then see what the process is so that you can generalize it with variables later. So we have two different things that we're comparing here. So I labeled my diagram. I said the radius of the cup was going to be 10 units and the height of it was going to be 20 units. I don't know what the water dimensions are going to be, so I just said lowercase r and h there. So I have two different things that I'm looking at here. One of them is the volume of the cone, which I know is 1/3 pi and then r squared, so 10 squared times h, which was 20. So that comes out to be 1/3 pi times 2,000, or 2,000 pi over 3. Right? We also were comparing the volume of the water. Okay? And here you can see that the volume of the water, it's a cone also, so it's 1/3 pi r squared h, lower cases on those. So when I'm looking at this thing here, you have a couple different options for how you want to go through this, but one of the things that I'm going to be looking at here is I need to have a way to compare r and h. Like, how do those relate to the radius of the cup and the height of the cup? Well, if we take a look at the two different things, the two different triangles here, we essentially have two similar triangles. One of them with the cone here, where this is 10 and this is 20, and then we have the smaller one, which is the water. I'm using the right angles because it's easier to work with the right triangles here, but this is h and this is going to be r. Now we know that these are going to be similar triangles because they share two angles right there, or have two congruent triangles or angles right there. So these are similar shapes. So here I can go ahead and say that 20 to 10, so it's the height over the base, is equal to the height over the base of the small one. Right? So this one just reduces down to 2 over 1 instead of h over r. And now if I want to get r by itself here, or h by itself, I'm going to go ahead and get r by itself, because what I want to do here is I want to go ahead and get r by itself so I can make a substitution and have r go away, so I'm just left with h. Okay? So if you take a look at what I do have, is I have this expression for r, and I have r in this equation over here. If I make a substitution there, I have 1/3 pi, and instead of r, I'm putting in h over 2. I'm going to square that times h. So when I simplify all this out, I'm going to end up with 1/3 pi h squared over 4, because I square both numerator and denominator, times h. It's kind of a mess right there, so I'm going to go ahead and just clean it up a bit and write this as pi h cubed over 12. Okay. So that's great. Now we have the expression for the volume of the water, just in terms of one variable. But keep in mind what we're trying to do. We're trying to compare the height of the water, or the depth of water, to the height of the cone. Like, what percentage of it is it being used here? So in this case right here, we also know that the other piece of information we haven't used is that the volume of the water is half the capacity of the cone, which means that we can also say that the volume of the water is equal to 1/2 the volume of the cone. Okay? And in this case, we have an expression for the volume of the cone, which is up top there, which is the 2,000 pi over 3. And so 2 goes into 2,000 1,000 times, right? So I end up with 1,000 pi over 3. So if you take a look, we've got two expressions here for the same thing, which is the volume of the water. So you have two things that are equal to each other, we can set them equal to each other. So pi h cubed over 12 equals to 1,000 pi over 3. Totally up to you how you want to go through this thing. When I have a fraction equal to a fraction, I usually cross multiply to get rid of those fractions. I think things are a little bit easier to move around and manipulate if we don't have those fractions. Okay. So as I look here, I can divide both sides by 3 pi, right? 3 pi. 3 goes into 12 4 times, and the pi's cancel out. So I'm left with h cubed equals to 4,000, or 4 times 1,000, right? So in this case, I want h by itself, so I take the cube root of both sides. Now, here, the cube root of 4 doesn't work out very well, right? It doesn't come out to be an integer value, but cube root of 1,000 is just 10. Remember, it's what same three numbers multiply together to give you 1,000, so that's 10. So I have the height now. I actually have an expression for it, and there's no variables in it. So remember, keep in mind what we're trying to compare here. It was the height of the water, h, over capital H, which is the height of the cone. So I know that the height of the water is 10 cube root of 4. And then in the beginning, I wrote down that the height of the cone was going to be 20. So here, 20 goes into 10 two times, and I'm left with the cube root of 4 over 2. Okay? And if you type that into your calculator, what you're going to find is that this comes out to be approximately 0.7937, which if we change that to a percent, comes out to be 79.37%. Okay? Now, we can try to figure out how to make that work with all variables. Good luck.